Hello and welcome to the Edexcel Further Maths videos for Mechanics 1. This is Elastic Springs and Strings. This is video 1.1, Hooke's Law. Okay, so far we've made the modelling assumption that all strings are extensible, so they can't be stretched. It's a great assumption to use for lots of situations because usually the extension of the spring can be very small and it has a negligible effect on the problem. However, some objects are actually designed to be stretchy, and if that's the case, we need to take into account their elasticity. So in this section, we will deal with both elastic strings and elastic springs. There's only a small difference between them. Elastic strings that extend when they are pulled, and therefore they can only be in tension. However, with a spring, they can extend when they're pulled or when they are pushed, so they can be in tension or compression. For many materials, we can use Hooke's law to provide a really good model of their behaviour when stretched. And Hooke's law states that the extension is directly proportional to the force applied. And that means that we can see if we graph the force against the extension, we get a straight line. 0 when the extension is 0, and when you double the force, you double the extension. So here, to get this extension of x, we're going to add a weight w, and to get this extension of 2x, we will need a weight of 2w. So here we have Hooke's law. The force is lambda x over L. In this particular, well, in all cases, lambda is the modulus of elasticity of the material, and it has units newtons. L is the natural length of the spring or string. So this is before it has been extended. So on this diagram here, the natural length L would be there. And X is the extension in the spring or string. You may have seen F equals Kx, where K is referred to as the spring constant or stiffness. However, you really don't want to get K and lambda mixed up. We use lambda. K is more used in physics. So let's have an example now. We've got a light elastic string of natural length 1.5 meters and a modulus of elasticity 50 newtons being stretched to a length of 2 meters, and we want to find the tension in the string. So we know that lambda is 50, L is 1.5, and X, the extension of the string, is 0.5. Remember that it's the extension, don't be tempted to put in this 2 meters. So tension, our force, is lambda x over L. So that is 50 times 0.5 divided by 1.5, which gives us a tension of 16.7 newtons to 3 significant figures. Okay, so here's our second example. We have an object of mass 0.5 kilograms. So acting downwards, we have 0.5 g, and then an equal and opposite t, hanging from a light elastic string of natural length 15 centimeters. The object's hanging in equilibrium 18 centimeters below the point of suspension. So the natural length of our string is 15 centimeters, which means our extension is 3 centimeters. So in this case, we don't know what lambda is and we don't know what t is, so we're going to need to work out t first. So because it's acting in equilibrium, or it's hanging at equilibrium, we have t minus 0.5 g must be 0, so t is 0.5 g. I tend to leave my g's in right until the end. Sometimes they cancel, and it's certainly a lot easier than actually having to write out the number. So now we need to move on and look at Hooke's law. So we have L is 0.15, we're going to use meters here, X is 0.03, and T is 0.5 g. So we have 0.5 g equals lambda times 0.03, all over 0.15. And if we rearrange this, we find out that lambda, the modulus of elasticity, is 24.5 newtons.
So now we're going to have a look at an example of compression, and we can see here that a block here of mass 4 kilograms is on a light spring of natural length 20 centimeters, 0.2 meters, and modulus of elasticity 300 newtons. And we want to calculate the change in length of the string. So what we have here acting down is 4G, and then the tension in the spring. So we have T equals 4G because we are at rest at the moment. So if we then put that into our formula, T is lambda x over L. So 4G equals 300 times x. Remembering in this case, x is going to be how much the spring has been compressed rather than extended, all over L, which is 0.2. We get x is 0.0261, which means the spring has been compressed by 2.61 centimeters. So on to a slightly more complicated example now. Now we're going to have to deal with some angles as well as some tensions and elasticity. So first of all, we're going to do a bit of geometry here because we need to find out what this angle here is. Now these two strings, you can see, both have natural length 1 and have the same modulus of elasticity. So when they are hanging this object here of 20 newtons, they're both going to be extended by the same amount, and that means that we can look at this as a right angled triangle of sides 1.2 and 0.5, and then we can try and find this angle here. So we know that tan alpha is 0.5 over 1.2, so we find that that angle is 22.6 degrees. We also want to find this length here so that we can find out how much the string has been extended by. So if we call this point x, we can just use Pythagoras. So the distance bx squared is 1.2 squared plus 0.5 squared. So we find that bx is 1.3 meters. Remember, we're interested in how much the string has been extended, so that means it's been extended by 0.3 meters. So now that we have all of this information, we've got 20 newtons acting that way, same tension in both of the strings. We know that x is 0.3, that L is 1, and that lambda is what we're trying to find out. So now if we look here, we can see that these are the same. So we've got 2t sine 22.6 must equal this 20 Newton weight that's hanging down. So when we rearrange and solve, we find that the tension is 26 newtons. And now we can use Hooke's law, lambda x over L. So 26 is lambda times 0.3 over 1. So we find that the modulus of elasticity is 86.7 newtons. Okay, so please join us next time for 1.2 elastic potential energy.